Check out this cool experiment. I'm shining my laser light through 2 glasses of distilled water. To this glass, I've already added some sugar and stirred it very nicely so it's dissolved. To this glass, I have not added anything. Notice that we don't see the beam or the path of light in either of the glasses. But now we'll go ahead and add some milk to the second glass. And notice what happens. As we stir that milk, we can now see the path of light. So the question is, why do we see the path of light when we add milk, but we don't see it when we add sugar to it? So the reason we get to see the path of light in this milk-water mixture is due to a phenomenon called scattering of light. So scattering of light. So let's see what happens. When we add milk over here, the milk particles get completely dispersed throughout the medium. They distribute themselves throughout water. And now when light enters into this mixture, it hits one of these particles. So let's draw that over here. So here's our light. Let's say this is the light from the laser. It enters into this mixture and hits one of these milk particles. So here's one of that milk particles. What happens after this is the milk particle reflects this light in all the directions. So it reflects light in all the directions. And the important thing to note over here is earlier we have seen that big objects like mirrors or a ball or any big object, if you take, they will reflect light in a specific direction. But turns out that when you get to these really tiny particles, they will always reflect light in all the directions. And if you're wondering why this happens, then it turns out we need to really dig into this deeper and figure out how light interacts with matter and everything, which we'll not do. So we'll just accept that tiny particles, this is the property of tiny particles. They will always reflect light in all directions. It's just that when these tiny particles get together to form a large object like the mirror or any other day-to-day life object that we encounter, then they only tend to reflect light in a specific direction. Okay, so this phenomenon of reflecting light in all directions is what we call the scattering of light. And because of this, some of the light is also reflected towards us. We are somewhere over here. I can't draw that over here. We are somewhere over here, right? That's where the camera is. So some of the light gets reflected towards us or into the camera. And as a result, that particle, we see that particle glowing red in color. It glows red because it's reflecting red. And therefore, that particle which it hit over here, that particular particle glows red. And then of course, not all the light gets reflected. Some of the light goes through as well. Actually, most of the light goes through. Let's draw that. So most of the light goes through. This is the light that didn't get scattered. Got that? This is the scattered light, and this is the light that didn't get scattered. So most of the light goes through, and then it hits another particle, and then again scatters off from that. So another particle over here will glow, and the same process continues, and as a result, all the particles which are in the path of that light end up glowing. And since these particles are really, really tiny, of course I've drawn them to be pretty big over here, but they are really, really tiny, and there are so many of them that when we look at it, we don't get to see the individual particles, but all we see is a straight line. So we see a line that is glowing, and that line is what we perceive as the beam of light. That's that beam that we're seeing. So what we are actually seeing are the milk particles who are scattering light, and as a result, they're glowing. And that's what shows the path of light. But why don't we see the path of light in a sugar solution? Don't they scatter light? Well, they too scatter light. In fact, all particles tend to scatter light. But here's the thing. It turns out that if we do the analysis, it turns out that the amount of light that they scatter depends on the size of the particle. As the particle size becomes bigger and bigger, they tend to scatter more and more light. If the particle size becomes too small, then they do scatter light, but that scattered light will be so insignificant that we won't be able to see it. So considerable amount of light will not reach our camera. And that's what's happening over here. The particles in the sugar solution are so tiny that the scattered light is negligible, and that's why we can't see it. And in fact, analysis shows that if the particle size is roughly, if the size of the particle is roughly smaller than 1 nanometer, all right, this is not an exact value, it's a rough value. If particle size get any smaller than a nanometer, then their scattering effect is so tiny that when you shine light through it, we won't be able to see anything. And that's what happens in any solution. So you take sugar solution or you take salt solution, whenever something dissolves, those particles usually tend to be smaller than a nanometer, and that's why we don't see the path of light. But milk particles are way bigger than a nanometer. They could be about, I don't know, maybe, I don't know the exact value, but maybe around 60, 70 to 100 nanometers in size. On the other hand, if the particles become too large, so let's say we have particles which are too large, and again, a rough value would be, let's say they're about larger than about 1,000 nanometers. If they get too big, then also we have a problem. Their problem is not with scattering. These particles can scatter light even more strongly because they are big particles. And by the way, an example of this would be dust particles. And you may have seen that sometimes when it's dusty and you're outside, it's nighttime, and there are vehicles with their headlights, you can see the beam of the headlight, right? That's an example of scattering of light by big particles, like dust particles. So they don't have a problem with scattering light. But their problem is, since they are too big, they tend to usually settle down due to gravity. So if we were to add dust to water, which we will do in a minute, we'll look at that in a minute, then even if you stir it very nicely, those dust particles will not stay long in the water through the bulk of the water. They will usually tend to settle down. And once they settle down, then most of the particles won't be in the path of light. And that's the reason they won't scatter light. So the ideal case for us to see a path of light would be to have particles whose size is somewhere in between this. So if we have particles which are not too small, their size is larger than a nanometer, but they're not too big so that they would settle down. They're smaller than, let's say, about 1,000 nanometer. And by the way, remember, these are rough values, okay? Then we will get to see the path of light. And such cases, such mixtures are called colloids. So, okay, it's a little hard to see. So let me write that down over here. So it's called colloids. And you may have already studied about colloids in chemistry, the same colloids we're talking about. So colloids are the best example to see the path of light. These are called as solutions. Solutions are one of the worst to see the path of light because the particles are very tiny. Sugar solution, salt solution are examples of this. And these are called suspensions. They too scatter light very strongly, but the problem is they tend to settle down and usually not be found in the path of light. So if we go back to our experiment where the sugar solution is not showing us the path of light, if we look at it carefully, you can sort of see the beam, isn't it? Now this is not due to the sugar solution, don't worry. If we zoom in carefully, we can actually find the particles which are scattering light. You can see there are some dust particles that got also added when I added the sugar and some impurities. These are the particles which are larger than the 1,000 nanometer size. So that is causing a suspension. So the scattering that we are seeing over here is due to these suspended impurities. And by the way, look at this dust particle which you can see over here. That is so large, we can even see it with our eyes directly. And as it swirls and comes into the path of light, notice how strongly it scatters light, okay? Just concentrate on this particle. Let's go back a little bit. Just concentrate on that particle. Here it is. Look at that. Look at that. Do you see it? See how strongly it scatters light. So big particles can scatter light, no problem. But their problem is that they tend to settle down. So most of those particles will not be found in the path of the light. And as a result, their scattering or their path is not so strong. It's nothing compared to what we see in colloids. So colloids are the ideal place to see this effect. So that's pretty much it. One last detail is whenever we have scattering of light due to colloidal particles, due to colloids, we often call that as the Tyndall effect. So scattering of light due to colloids is called Tyndall scattering or Tyndall effect, because this guy John Tyndall did a lot of work on this subject. And this also has a great application. Tomorrow, if we have any mixture and we want to know whether it's a colloid or not, we will just shine light through it. If we can see the path of light, that's Tyndall effect, then it's a colloid.